Bismillah ar-Rahman ar-Rahim. Welcome back to our course on deep learning for computer vision. Today we'll continue our work on machine learning part, and specifically we are going to discuss selected machine learning algorithms. Specifically, we'll discuss the super vector machine. Also, we'll discuss the k nearest neighbor algorithm, and finally we'll have a look on the k-means algorithm. So let's jump to our lecture slides and start talking about this issue. As you see from the title, we are going to talk about various machine learning algorithms. And we'll start with the session guidelines. We'll have a quick tour on machine learning. Then we'll talk about super vector machine algorithm. And next we'll talk about the k nearest neighbor algorithm. And finally, we'll have a look on the k-means algorithm. Of course, this part has been discussed earlier, and we'll just want to recap or have a summary of what we have discussed before. So machine learning is a branch of artificial intelligence that is concerned with developing models and algorithms for computer applications to learn from the data without the intervention of humans. And this means that we can develop learning algorithms that teaches from this system itself, and it looks like it has its own thinking and it understands like the human, and it mimics the human, let's say, thinking procedures. In general, the main issue in machine learning is to have a good training part of the system. When you have a good training of the input data set, you can develop your system and deploy it in other applications. So in the training stage, we are trying to let the system learn its own parameters, like the weights and the biases, and develop an output that is very close to the predicted output, or from the true output that was designed before. If you remember from previous lectures, we have in machine learning, we have supervised learning, unsupervised learning, semi-supervised learning, and finally reinforcement learning. This was discussed in details in a previous lecture, and today we are just going to repeat very quickly some of the main concepts of these things. Now, for supervised learning, in this case, we have mainly the system has been trained, or we can say that it has a supervision type of learning, where the output is well known from the beginning, and we try to modify our weights and biases in respect to the inputs applied to it by having, or by a supervision with having the output, let's say, classes or maybe regression issues known from before we start our training. We also discussed in previous lectures techniques that can be used in supervised learning, like logistic regression, support vector machine. These are examples on supervised learning in machine learning, random forest technique, decision tree algorithm, k-nearest neighbor, and naive Bayes. And you can have a look on these links to get some info about these techniques. The second type is the unsupervised learning, where we don't have from the beginning, we don't know exactly what are the classes maybe, or the results of the machine learning task, and we try to figure out and find and develop our learning regarding the weights and the biases in our system, and try to improve the performance by reaching a high level of accuracy at the output of the inputs for the given dataset at the training stage. Examples on the unsupervised learning applications: k-means clustering algorithm, mean shift algorithm, DB scan, principal component analysis, PCA, independent component analysis, ICA. So you can also refer to these links in order to get some additional information about these techniques. In the simple supervised learning algorithm, here we have a part which is supervised. We have another part which is unsupervised. Usually, when we have tasks that the data annotation, or what we call the labeling of the data, is not easy. It may be a big hassle due to many issues like the huge data size, maybe due to the difficulty in accessing this data. In this case, we may label a part of the data set and leave the other part unlabeled, and we can use the supervised part in order to learn or to let the system or the algorithm learn for the unsupervised part, and this will lead to have what we call it the semi-supervised learning algorithm. Examples of that, we can find graph-based SSL, label propagation SSL, co-training SSL, self-training SSL. As you see that semi-supervised learning is based on these types. Also, this is a very important part of semi-supervised learning is the generative adversarial network SSL. Here we can generate fake data that can be helpful in order to enrich or to increase or to augment the data set at the input, or maybe to apply other applications. However, you have a good luck if you can go to these links and see what's about this story or this full technique. In reinforcement learning, we try to learn from errors or from fails and get, let's say, a sort of winning when we have a good output or a good choice in our action. So the agent is going to learn more and more during the time and will be able to improve its performance with time. Techniques are, examples on these techniques are the Q-learning, the SARSA technique, the deep Q-learning, and it can be, for sure, you can see these links and have a look on these websites, mainly from Geeks for Geeks. It's very, very simple and very straightforward for beginners to understand the main ideas behind the reinforcement learning algorithm, as well as for other learning algorithms approaches. Let's start with the first type, with the first example in today's lecture is the support vector machine, SVM. So SVM is a supervised machine learning. First, it's a supervised learning method. So we have here a supervised technique, okay, used for both classification and regression. So we can use it for classification, as you see here, and also we can use it for regression. It's the main idea behind the SVM technique or algorithm. The SVM actually is a very strong machine learning algorithm that can be able to, let's say, apply machine learning to linear and nonlinear classification or regression tasks. So when you have the input data, whether it is linear or nonlinear, you want to apply it for classification or for regression. In this case, SVM will be very helpful, and it actually gives, in general, as I have an experience regarding this issue, it gives you a very high performance at the output for both cases, whether you have a classification or regression task, and the same thing, we don't care whether the input is linear or nonlinear. Where we can find applications for this, as you see here from this slide, you can see that we have here, it can be used for many tasks like text and image classification, maybe for spam detection in emails and in messages, for gene expression analysis, it's in medical applications, in face detection, face detection and object detection issues, and in anomaly detection, when you have some anomaly detection, especially in medical applications, when you are dealing with, let's say, cancer or maybe some other problems or medical diseases. And in this case, you can use SVM very efficiently to classify or to regret or to have the regression task at the output. Another key feature for the SVM is in the fact that it's adaptable, which means that you can adapt your SVM according to your application. If you have a different application, you can adapt it to the new task that was not before, let's say, trained before. So it can be considered as an adaptive machine learning tool, and it's very effective in terms of its parameters and its output performance. It can be used, as we have seen here, we have a lot of applications regarding that where we can use the machine learning approach in it. So mainly why it is adaptable and efficient, because the SVM usually is working in this way. It tries to manage or to deal with high dimensional data and try to reduce the dimensionality of this data and try to extract or get features from the nonlinear relationships in the data itself. So this is why it is considered as a very important and well-known machine learning technique. Again, it's a supervised machine learning technique, powerful for classification for regression. It's also can handle both linear and nonlinear data sets or let's say data inputs, and this is why it can be it works with very high dimensional data sets, and this is one of the key features, crucial points for the SVM to be a very known machine learning technique. Here, how it works, mainly the main objective of the SVM is to find the optimal hyperplane. The optimal hyperplane. We'll see this on the next slide. Here, we usually have the data given in n-dimensional space, okay? And we try to separate the data according to the data points into different classes, for example, in case of classification, according to the feature space, not according to the data space. As we have mentioned before, it can be used for many applications. It is also adapted to various types of data at the input. Let's go to this simple example. Suppose that you have two types of, let's say, or two classes of with blue balls and red balls, and here we have the input x1 and x2, and these are the dataset values. So the x1 and x2 can be classified either as blue or as red. Now we try to use the super vector machine in order to split or to find clusters or to define classes for this data. When using SVM, we start with this starting stage here. We try now to construct a hyperplane that divides the objects into two. Let's say we have two classes, with a condition that the hyperplane must be, as you see on the next here, maximum margin hyperplane, or we call it as a hard margin. What we mean by this, the margin between the closest points of different classes should be as maximum as possible. What does that mean? So you have to select the hyperplane here, this hyperplane, this one. You have to select it in order to get the highest distance from the nearest samples in the two classes. For example, if we have just two classes. So if you select this one, you see that it is the values here is not maximum, while for this maybe it's maximum. So you try to maximize the distance or the difference between the closest samples to the classification border or to the hyperplane. This is the main idea behind using the super vector machine. So in this case, you see that the data is two-dimensional, while the hyperplane is one-dimensional. So it is a sort of reduction in dimensionality of the when dealing with the data in this case. So let's start with this figure. Suppose that we have some samples that are classified as blue ball in between the red balls. So this type of data is a little bit complex because we cannot distinguish and separate this blue ball from the surrounding or the neighboring, let's say, red balls. Here, this is an outlier sample. We call it as an outlier sample, and it is ignored by SVM. We usually ignore such samples because they will, if we assume and consider it in our calculations and defining the hyperplane, it will lead to a very sophisticated output steps, and this will complicate our technique. So in this case, we can just ignore the outlier samples and try to bypass more or less this way. So our hyperplane will be something like this one here in this line, as you see here. This is the line that where we can sketch the hyperplane, and this is what we, regardless of the existence of this sample that is included within the cluster or the class of the red balls. Nevertheless, it belongs to the class of X2 or maybe the blue balls. Of course, it's the maximum margin. It's a sort of penalty. It adds a penalty each time a point crosses the margin. So here we have a penalty having this blue ball on the region of the red balls. So this type of margin is called a soft margin issue or application approach. What is the type of loss that we want to calculate? How to find the distance or the loss? In this case, we use the Henk loss, which is a commonly used penalty that is proportional to the distance of violation. So this is considered as a violation. As you see here, this is considered as a violation to the class, let's say, of blue balls, red balls, and to the class of blue balls. So this violation can be measured and found using the Henk loss that can be calculated for these balls and for these samples as well. If we go to the Henk loss, it can be defined as you see here. It's the loss of y, the output is equal to max between 0, 1 minus t, and y. Now, 0 it's clear and cut. For the t variable here, this t value usually takes a value of either plus or, let's say, plus 1 or minus 1. So it belongs to one class or to another class. We now apply 1 minus t. According to this, we get a value. So we have a 0 and 1 minus t. And the y value that is obtained as a classifier score output. This is the classifier score can be embedded here, and we find the loss appropriately or consequently. Now, we need to update the parameters. In this case, if we are talking about the W parameter, it will be updated one of these two methods or approaches. First time, if we have no misclassification, so if we don't have any red ball in between the blue balls, for example, we can go to the second part, to B, to the first part, A, with no misclassification. So we do not have misclassification, let's say balls or samples, so we can update the, according to the support vector machine, W as W minus alpha multiplied by 2 lambda W. Now, alpha is the learning rate, and lambda is a hyperparameter added by the SVM technique. With misclassification, we modify this by adding the value of x1 and the y output y1 to the multiplicand here by alpha. And during this process, we can repeat and iterate until we reach a specific learning rate at the output or a specific, let's say, minimum value for the loss. Here we have different types of SVM. Of course, here we have many modifications of SVM. We have linear SVM, quadratic, cubic, and other polynomial types for SVM. Of course, you can have some links and see at the end of this lecture, you can see some YouTube videos regarding the SVM, higher order techniques for SVM. Here you can see, if I can zoom it for you a little bit, because maybe this is the input data. I see that we have the scatter diagram for the input data. Here we have two values, either -1 and as you see here, we have -1 and 1. So the red is -1 and 1, and the blue is -1. This is 1 and this is -1. So this is the data scattered in the scatter plot for the data. Now, if we go and see the result of applying the support vector machine, we can see that here we have the white big ball. It represents the support vectors that has been used to divide the data into into these classes. So you can see that it may be not very clear, but you can see that this part belongs, with this part belongs to the red to the blue balls, and this is the first class, and maybe this one belongs to the second class or cluster, while these balls here with these red and maybe blue small circles inside the white circle are relying on the border of the support vector machine hyperplanes. You can see also these things here regarding this topic, and I just tried to explain it in general, the main concept, and when you go deep in details, you can find much more details. Of course, you may find also it's very well programmed technique. You can find it in MATLAB, in Python, in PyTorch, in all these programming tools. You can find it with different versions, linear, cubic, etc. And we'll see a tutorial on the next lecture regarding this machine learning type, which is SVM in general. Let's go to the second type. Here we have the K nearest neighbor or KNN algorithm. What is KNN? KNN is a simple, easy to implement supervised machine learning algorithm. So again, it's a supervised machine learning algorithm that can be used to solve both classification again and regression. So you can use KNN for regression as well as for the classification approaches or tools or tasks. Let's have a look on this data. Let's zoom it a little bit. So we have here two types, again, x1 and x2 of samples. We know that we have these clusters here. More or less, it's maybe visible for you now, but for a computer, it will not be very visible. We now try to define that this new data sample, whether it belongs to this class, for example, or to this class. Okay, and this will be defined using KNN easily. Okay. Okay. Now the KNN assumes that similar things exist in a close proximity. So this is very ideal situation. For example, we all know that the in-joke or the legend, birds of a feather flock together. So they are combined, or they are making a team together, and they occupy the almost the same or very close proximity for when flying and when landing, etc. So the main topic or main idea behind KNN is to use this basic idea in defining the whether the samples belong to this or to that clustering or cluster, or maybe a class. So how it works? It just tries to, by finding the k nearest neighbors to a given data point based on a distance metric, such as gradient distance, maybe other types of distances can be used. So we try to find whether this sample belongs to this or to that class by finding the closest or the smallest error or maybe distance from this or that class samples. In classification task, the class or value of the data point is then calculated or defined by the majority vote or average of the k neighbors, either by majority vote, we'll see this in the next slides, or by the average of the k neighbors. In regression task, the label is calculated by taking the average, always by taking the average of the k means k nearest neighbors. So we have here to distinguish between two types of tasks. If we have a classification task, we can use either the majority vote or the average. While in case of the regression, we need to deal with all the time with the average of the target of the k nearest neighbors. And this is actually very important to distinguish between the two types of tasks. Now, what is k? K is the number of selected neighbors to be included in distance calculations. So when you select k equals 2, this means that you are going just to include 2 neighbors. If you take k equals 10, you are including 10 neighbors, and so forth. What are the distance metrics that can be used in KNN? There is a long list of metrics. It looks like other machine learning algorithms. Maybe this one, this metric will be suitable for this type. The other one will be to the another type of algorithms. However, we have few very well-known, let's say, measures for the distance. I have summarized in 3 types here: Minkowski distance, Euclidean distance, and Manhattan distance. Let's have a look, closer look on these distances. Here we have the Minkowski distance. So we need to measure the distance between, let's say, 2 samples. Here, this one and this one, having the coordinates xj1, j2, etc. into 3-dimensional, maybe more or less. Here, with I1, x1, I1, xi2, I3, etc. What we do is we take the kth root of the difference, the absolute error between these 2 samples or the coordinates. Then with the absolute value of the error or the difference between the 2 coordinates, and so forth until we find the, of course, always we rise this to the power k and take the qth root to the power q, and we take the kth root of the overall of this absolute values. Now, if we have 1-dimensional, we just take this one. If we have 2-dimensional, we may take this one and this one, etc. Usually we take maybe up to 2 or 3 dimensions, and this is why we may stop at p equals, in this case, equals 3, maybe as a max in most of our applications. In the Euclidean instance, the q value is limited to the to 2. So we take the square root of only two second order of these differences between these coordinates. In Manhattan distance, like a special case of Minkowski with q having only 1. So we remove this square root or kth root or qth root, and we just keep the absolute difference or between the coordinates of the two samples x1 or xj and xi. Okay, this is the main idea behind the distance measures or metrics in this situation. And in general, we want now to calculate. We have a sample here and want to find whether it belongs to class A or class B or class C. And here we may use the k nearest neighbors in order to find the belongingness of P to one of these classes. Okay. Let's start with steps. How we can do this? Step one, let's say that we want to classify the gray point here to one of the other two classes here with the, let's say here we have lime green class and blue, green class and maybe the orange or the brown class. So this is our task, what we want to do. Now we can include, as you see here, we can calculate the distances between the gray point and all other points in this data set. Next, to find neighbors, we now order the nearest neighbors by ranking the points by increasing distance in ascending order. So as you see here, we have, for example, for the distance with this point, the first nearest neighbor is 2.1, second nearest neighbor 2.4. So we order it and we keep in mind what is the type of the class of these points. Of course, here we use the distance. Let me a little bit zoom this part. Of course, we used here different types of distances. We may use the Minkowski in general. We may use the Euclidean distance, or maybe just the first order or the absolute error distance to find these values. So these values can be found according to the type of distance that metric that has been used in this regard. Okay, next. Let's go back to the original size. Now we need to vote on labels. What does that mean? So we need to find or to vote, as here. For example, if we we look at this part of work, we have here two balls from the lime green class. So we have the vote shows that we have two, number of votes is 2, and the class, this class which is lime green has 2 votes. If we continue, find that the green has 1 vote, we have only 1 vote, and so forth. We may continue until we reach all. So, however, we don't need to continue to the end of all, or to include all the values. It depends on the value of k. What is the value of k that we want to select in this situation? So don't forget about k. What is k in this situation? For example, here we have used k equals 3. We may say that we have used here k equals 3. So in this case, we take only the first 3 highest or lowest distances with the surrounding samples of different classes. Let's talk about this. This may give a better. Sorry, we'll go back to this slide again. So if we have a look on this graph here, you see that when we include, if we include now only, we take 3 nearest neighbors. So k equals, we take this is our sample. We have 1, 2, and 3 samples from different classes. So in this case, we take only k equals 3. Okay. Next, we may increase this k to be, let's say, 7. So we enlarge, and the vote will be done according to these values. Now, if you look at k equal, when we have k equals 3, the vote mainly will lead to make this sample belong to class B. While when we take k equals 7, so if you see here, we have 3 samples, and we have here 4 samples, so the vote will be making the sample belonging to class A. So what does that mean? We need to modify and change our k value in order to get the best results and to get the output that is required in this situation. After finishing our work, we can apply, we can do the process by selecting a proper, let's say, a proper k value. So this is k equals 3, it's k equals 7. Let's remove this one. Now let's go to the last algorithm, the k-means clustering algorithm. It's actually another type of clustering technique. It is unsupervised learning, where we don't know exactly from the beginning what will be the outputs, and it groups the unlabeled data set into different clusters. So we can use it in clustering, as well seen from the title or from the definition of the this scheme or the algorithm. It's k-means algorithm. Now let's go further. So it's an unsupervised learning technique. It can group unlabeled data set into different clusters. Now k defines the number of predefined clusters. So how many clusters you want to use for clustering your data? You can vary this value, and you can select it either optimally or empirically. The same thing for k and n. You can select k there by the number of votes or by the number of included samples in the k and n scheme. Similarly, here we have to select the number of clusters and must be predefined. So you can repeat the process many times and get a final or an optimal solution, or maybe a compromise solution for k. And this can be repeated many times to get this proper k. So k plays a vital role in this regard. Here we have unlabeled data. We have circles, triangles, etc. And want to classify into groups or into clusters according to the machine that we are doing here, which is the k-means procedure to be applied. Here we have the data in green color. All the data is given. We try to use k-means algorithm. It's clear that the very nice to have or very properly can be obtained in clusters using k equals 3. But this is not the issue every time. You have to modify according to your data, because sometimes there is no separate lines between the data samples, and this will be very little bit will complicate our task. So here k equals 3, as I just mentioned. Now, k-means algorithm is an iterative algorithm, so it repeats the process until we reach a specific threshold or a value. So it divides the unlabeled dataset into k different clusters in such a way that each cluster dataset belongs to only one group that has similar properties. What does that mean? So we divide the input dataset into the unlabeled dataset into groups or clusters. How many groups? We have k different clusters in such a way that the samples in the dataset will belong, every sample in the dataset will belong to a specific cluster or group that has similar properties, So here we have the steps of the k-means algorithm. Here we select the number k to decide the number of clusters, select k random points, we call it the centroids. Now we assign each data point to their closest centroids, calculate the variance or place a new cluster centroid, modify the centroid locations, reassign each data point. Again, if reassignment is okay and there's no modification, we stop. Otherwise, we need to repeat and go to step 4 and repeat the process until we get a fine or an acceptable output. And this way, the model will finish its work and it will get a final decision. Let's start with a simple case. It's having two variables, M1 and M2, and its k equals take k set or equal to 2. So here we have the data set, a labeled data set. Now we choose some random k points or centroids. The centroids represent the center of gravity of every cluster at the output. So we roughly now going to select two clusters, as you here. We selected this cluster centroid, and this is the cluster centroid for the. Now, as you see that the clusters are not very properly selected because we may divide this into one centroid at this point, or two classes, this one class, and then second class, maybe. And the centroid may be somewhere here or there, and or maybe for this one at this location. The process is random, so we can select it randomly from the beginning because it will be updated and fine-tuned. Now, centroids are selected randomly and can be out of the data points. So it's not a must to have the centroid, for example, to be overlaid or to be selected as one of the random of the samples here or there, maybe. So it has been selected roughly at these locations, and they are out of the data points, Next. Now we try to cluster the data points into these two centroid or two clusters by means of distance between the data points and the centroids. So we calculate the distance between these centroids and the data in the surrounding data set, samples of the data set, and then we define the clusters in this case. So this is the centroids and the data points. We calculate the error or the distance, and finally we may draw a mean between the two centroids. As you see here, this is the mean line, and the confinement. This means that we have here, this is one cluster, and this is the second cluster. Of course, we may use the mean line, the median line, or may use the distance thresholds. For example, this distance means that is lower than this distance. Lower than this one. So again, this one is lower than this one. For next, this one as a distance is lower than this one. So it is closer to this centroid than to this centroid. And we repeat the process for all data points. And this looks like that we cluster, give or classify these samples to cluster 1 or to centroid 1 and these samples to centroid 2. It looks like drawing a median line having between the two both centroids. Next, we repeat the process by choosing a new centroid. Now, the centroid, after defining the initial clusters, we find the new centroid by averaging, or maybe simply by averaging, or by finding the center of gravity of these centroids. This can be, of course, done by many ways, but this is the simplest way. This is the initial centroids. Now, the centroids have been moved as a result of applying averaging or center of gravity for this one, and this means that you have already get a new centroid value at this location for the first one and this location for the second one. This is just for demo applications. Next, we repeat the process again and define the median line or measure the centroids distances between the centroid and the data points and modify our clusters. So as you see here, we have new clusters. This is the first cluster, and this is the second one. According to the distances measured in this situation. For example, the distance between the centroid and this data sample is lower than the distance between this centroid and this data sample. This can be repeated for all data samples in this case. Now, here we have some critical cases, like these samples with the circles on it. This will lead to to reassign the data points. So these, from the previous case, when we measured the median line, or when we put the median line at this location, okay, we have got that some samples belonging to the blue, and they still have their situation that belong to centroid 1. The same thing here is true. It looks like it's closer to this one. What to do in this case? We need just to reassign the data point, the centroid with the data points. So these values will be this one has been converted from orange to blue, and this one has been converted as you see here from blue to orange. What I mean to say, after modifying the centroids, we recalculate the distances, and we find that some of the data that was belonging to centroid 1 has been moved to be belonging to centroid 2. And for the second centroid, the same thing is true. In this case, we modify, find the new centroid, and check the data. If the data samples have been changed to a new centroid or to a new cluster, this means that we need to continue and repeat the process again and again, unless we get a final decision that there is no change to be done. And if in this case, of course, we just modified the centroid locations and repeat the process, and for example, we get this situation. Finally, we reach this case where, as you see here, the last centroid at this location combines all the data or confines all the data samples, and there is no modification done when repeating the process. Here also the same thing, so we can stop at this point and see that this is the first centroid, this is the first cluster with its centroid, and this is the second cluster with its centroid. Now we may remove the centroids and leave the data as a final step being clustered and classified into these two clusters. Our work is done. Yes, no modification, no extra modification to be applied, and we stop at this point. Now, how to select the optimal value of K? Actually, there's a very well-known algorithms called elbow and silhouette methods. You can span the net and see what about this technique. In fact, the K-means algorithm has a lot of applications in communications, in electrical machines, and it can be used for when dealing with scattered data at the input in order to analyze and to get the data being clustered and classified into specific proper clusters and specific classes. Well, that's all talks for today, and I hope that you'll enjoy this tutorial. Please email me or send me, let's say, messages, and if you have any comments, I'll be very grateful to deal with these issues and to discuss these topics with you in person or maybe online. Thank you for listening, and see you soon, inshallah.